square root and get p squared minus q, and that's all over 2. Now the reason it's important that p squared is less than q is because that means that what's underneath the square root sign will be negative, and that will give you a complex answer. So we get x equals minus p plus or minus the square root of p squared minus q. And if we're going to make that into a format that we know exists, we're going to make it x equals minus p plus or minus, and we're going to take out a factor of minus 1, which changes it from p squared minus q to q minus p squared, because we're taking out I, so that we can represent it as a complex number in x plus iy form. Obviously, that is of benefit to us, and as we expected, because the coefficients up here are all real, that means that the two roots are complex conjugates of each other, exactly as we would expect. So what this basically looks like on a diagram is that you've got, assuming that at the moment p is positive, which isn't a guarantee, we've got minus p here, and then we're going up q minus p squared, so we've got a complex number there, and we're going down q minus p squared down here. There are our two answers. There are complex conjugates of each other. So that's for p is greater than 0, which makes negative p on the left hand side. Now if p is less than 0, meaning it's negative, then that actually does this same thing but in the opposite direction. So we've got two cases here that we're addressing, and what we're trying to figure out is how to make a right angle between these two. So here you want to make that pi on 2, or here you want to make that pi on 2. Now because they're complex conjugates, that forces each angle to be the same, which means that this has an argument of pi on 4 and this has an argument of pi on 4, or minus pi on 4. And over here the same thing is true. There's a pi on 4 between each root and the negative x-axis, but as an argument that becomes 3 pi on 4, because you always go from 0, and going the other way that becomes minus 3 pi on 4. My guess is that it won't change the relationship between p and q either way, but let's see what happens. So it's visually easy to see now that the argument when p is less than 0 is pi on 4, and that the argument when p is greater than 0 is 3 pi on 4. So now let's use that information about the argument to answer the question. We need a statement about the argument in order to find it. We know that the argument is pi on 4. We know how to find the argument. We have to be very careful about how we do that though, because the method of finding the argument isn't bulletproof. So our argument is q minus p squared square rooted, because we're taking the plus q minus p squared, and because p is less than 0, that actually puts that over p, because it becomes positive. But if you absolute value p, it doesn't matter whether p is positive or negative, and because we're forcing the argument to be positive pi on 4, that's helpful to put that there. The other way you can look at it is that the net result of p being less than 0 is that negative p is just a positive number, and taking mod p there, or absolute value of p, ensures that that's a positive answer by the end of it. Now, we know that that tan theta is equal to that. And we know that theta is pi on 4. And so we've got q minus p squared square rooted over absolute value p, or mod p, is equal to tan pi on 4, which is tan of pi on 4 is 1. So you're left with that statement. And then to make this true, we need to times this by both sides. Now, interestingly enough, to get mod p, we can actually do how do I explain this? So put that there like that, and then on the right hand side we've got p squared square rooted. Now the reason that's the same thing as absolute value p is because absolute value of p just takes off any sign, and doing p squared square rooted means by the end of that it's false positive, which is exactly the same thing that the absolute value does. Now the reason that's valuable is because now we can square both sides and get q minus p squared is equal to p squared, and then subtract p squared from both sides and get q minus 2p squared is equal to 0, which is the relationship required. Now the value in going to the other one of arg 3 pi on 4 is just that we know that in that case that p is positive, which we know means that we've got the answer being negative. So in a sense it doesn't really matter when you so the expression up here, the square root of q minus p squared over mod p, or absolute value p equals 1, works for both equations at the same time. So what I've done there is basically combine all of them and mean that in both cases q minus 2p squared equals 0 works. The other way you can look at it is that you can split it into the two cases and get the two different answers, but the sign will change either way. So for just to show you what I mean by that, for p is greater than 0, you get q minus p squared square rooted over negative p, but that's equal to minus 1. So in that case, you move the p across, you get q minus p squared square rooted equals p. Square both sides, q minus p squared equals p squared, as we got to in this line here. Now, you go the other way, for p is less than 0, and you get q minus p squared square rooted, and because p is less than 0, negative p, which is the x value, is equal to just p. And the argument on the right hand side, because that's tan pi on 4, is 1, and so you get to the same line, which is q minus p squared square rooted equals to p, and again q minus p squared equals p squared, so that's all good. Now, with all of that in mind, it doesn't matter, because for p is greater than 0, you've got tan of 3 pi on 4, which gives you minus 1 on the right hand side. For p is less than 0, you've got the right hand side, and that gives you an argument, tan of pi on 4, which is 1. So either way, in the wash, it requires q minus 2p squared equals 0.